Thank you, see you later. Okay, first have to get this running, all the setup. So good. So, hello everyone. It's always a little bit unusual with these clusters. I have to learn always how to look to all of you. So, welcome to this lecture, Circuit Design Fundamentals. As already announced, my name is Michael Piel, so I'm maybe a little bit of my background. I'm on a chair for security in information technology. So actually, we are working on hardware security. And so could you please stop discussions when I talk? Otherwise, I think it's pretty hard for everybody to understand. Okay, so I'm working on chair for hardware security. So what we do is hardware design for secure circuits. That's not the topic of this lecture here, but just to let you know. Good. What will we do in this lecture? So here, so that's more or less our agenda. It's not really necessary that we go through all of this, but it's effectively the 10 slide decks you already see in the X side, I think. I will start today with a little bit of background on the design flow. So how does actual circuit design, what are the different steps, what are the challenges there? And then we look into different aspects, starting with memories. I think that is relatively quick. Then we go into synchronization. That's, I think I switched this at first to synchronization. We have a little bit of ALUs, how they work. And then the components of ALUs, namely adders, counters, and so on, how they are implemented, which is partly algorithms, partly math, and always to connect to the circuit design. Good. From a time schedule, we have this week only lectures. That's how I plan it for the moment. Usually, after 1 or 2 days, I'm a little bit delayed, but we will finally make it, I think. For the next week, there on Wednesday, Jens Reupload will join us. He will do the tutorial, the exercises for this lecture. And then on 15 May, I will be done with the lecturing part. And you will have 1 week of only tutorial where Jens is with. Good, or 1.5 weeks. Then there are this year 2 separate days, which are online lectures, tutorials. There will be one tutorial mainly focused on Q&A on 3rd of June, and one mainly focused on Q&A, one lecture on 8th of June. Yeah? That's, I think, well, it's a new structure that is established this year. So we will see if how this works out. I think it's a good opportunity to ask questions or to discuss in preparation of the exam. Okay. Before we start, what you should already have is the slides for the lecture. We will have maybe some examples that I upload in the X site, and you will also get, likely end of this week or so, the first tutorial tasks that you can already look into. Afterwards, there should be recordings. Last year, I remember we had some problems with the recordings, that they were not automatically uploaded, something like this. So please let me know immediately if you do not find them. Then I tried to call the technical staff, and we will finally manage to. Okay, I will use this visualizer here for some stuff because, well, usually it's better to explain if I write something. And since we have here this different sides of the room and different directions, I think it's better to have this done with the visualizer than with the whiteboard. Okay, and whatever I write, I will most likely after the lecture usually, but maybe one day later also upload to the X site so that you also have this. Okay, we will have one or two practical examples I will give to you. The first one I will be with this Science Vivado. I may also use some Python code at some point. Nothing you need to use, but if you are interested in that, that are the tools we use. And the material is, of course, in X. Good. Then we have this year continuous assessment, which is new for us. So we was requested to do this, so we found something which I think is quite, could be quite good for you to help you with your learning process. What we request you to do is something we call a research diary or learning diary for the circuit design fundamentals. What does this mean? It means you're requested to formulate questions. Any questions? Or so you're able to formulate questions, or you should formulate questions to the lecture. I request you to ask at least 3 for the first, 3 for the second and third week. And you should propose an answer to that and reflect your learning process. That's the basic idea of such a learning diary. To be a little bit more specific, what we require as questions is you should write some questions that are specific, of course, to the topic, to this lecture. It should be self-contained, so it should be questions to the lecture which are self-contained, which are clear, and of course it should not be something, very, very trivial. With these questions, you should provide some reference what you actually refer to. You should focus on why something is or how something works, not on just simple questions like yes and no. And it should be non-trivial in the sense that you should not be able to just type 3 words in Google or wherever and find the answer immediately. That is how the question should look like. And then you should, for this assessment, for this CA, you should propose answers. The idea is that you immediately propose answers, but whatever you propose as an immediate answer will not be graded, but only the final answer will be graded. What's the idea behind this? The idea is you should have an actual question, you should have an actual idea what it actually could the answer be, and then you have the chance in our exercises, in the further lectures and so on, to ask these questions to Jens, to me, to discuss with your peers, just to find the real solution and to improve on your answer. For all the information you have, you should always provide some source of the information. So, did you have this from our lecturing context? Do you have this somewhere from the web and so on? You may, that I have later on the slides, also use some, don't know, ChatGPT, but if you use this, you should motivate why this, well, can maybe, have this here. If you use something like ChatGPT, you should always ask or give the information that you used it, and you should state why, if it's a question that you formulate with this, why this question is still relevant for you. I mean, if you only use it to formulate your question better, then it's perfectly fine. If you use it to find any questions to the course, maybe that's not the best way, but if it comes up with some question that is relevant to you, why not? If you use it to generate some answers, then you should always verify or always tell how you verified that this answer is actually correct. Because that's an urgent need in nowadays, let's say, AI-driven environment. I had this several times that I did some technical question, asked some technical question to this, and it was just wrong. Yeah? So if you use it, you should also verify the correctness, and you should state how you verified that. Okay, there should be to you visible already the first of the two CAs in the X side, where you can should be able to put pure text. Since we are doing this the first time, please let me know if something doesn't work. How much time do we have? The idea is that the first 3 questions are put into the system after the first 2 weeks. The second 3 questions are put into the system in a separate part in the second or third week. And you have then time till effectively end of the lectures to respond to. We will, if we see there are, well, I'll start differently. You will have the option also to propose your questions then for some, let's say, deeper discussion here in the classroom or in the online sessions later. And we will pick up some of them if we see there's something which we should urgently rediscuss. So that way, I think you benefit because you reflect the learning, you ask questions, you provide some answers. We have this connect between the lecture now and the exercise in the next week. And yes, after all, you can also get some credits for this, which is given here. So we have for each question, you get 2 points. So 2 points is equivalent to 1 credit. Then for the answers, if they are the final answers are correct, you get up to 2 points. And for the motivation, for this reflection and so on, you get also 1 point. So after all, 15 points, 7.5 credits for the exam, for the first 3 questions, for the second 3 questions, so overall 50 credits for the overall exam. Questions to that? So should be doable and should actually help you already in the learning process. So I think it's a win-win. Okay, before I start then with some content, is there any question on the administrative side? So regarding the exam, maybe 1 word. The exam will be a written exam at the end of or after the lecture time, I think in the week of 15th June, if I got it correctly, but that is not in our hands, so I cannot honestly say. The exam will be 90 minutes, and yes. No, we did not with cheat. So we just have a closed book exam. With a cheat sheet, that's always, well, if you're lucky, you have to write things in. If not, then not. With an open book, we do not do because we say then we have to ask the hard questions. So, good. Then we start with the actual technical content. Yes, maybe another thing for the preparation of the exam, we also usually do not provide the exams from the last year because there is no 100% overlap, but we have at the end, most likely here on the 26th, I assume, we will have a mock exam. So that you can have an idea what the kind of question is. And I say this every year, 90% or 50% of the students don't do this. Really goes through the mock exam, it will be in parts very close to the actual exam. So take this opportunity. Good. Now go to the wrong direction. Good. Then we start with the actual content, and what I want to do today is I want to take you through a quick run, let's say, through the design flow, to motivate a little bit where we will work on, what we require to understand, and yeah, how the overall big picture of where we work in looks like. And yeah, afterwards I will go into a little bit, most likely already in synchronization, but that will be already in the afternoon. Okay, good. I already had it shortly on the slides, but I stepped back for reasons. If I talk about, or maybe this one is okay. If I talk about the digital design flow, so we talk here in this lecture only about the digital design flow. I can give one or two words regarding analog design flow, but whatsoever. Then we have a lot of steps that are typically separated, where in between always there is a handover. As for any engineering system, I would say, we start with a system specification. So if you're an engineer at an industry, there's actually a specific type of engineers doing this. The first thing to do is you need to collect the requirements. You need to talk with your customer, collect what actually do I have to do, and have some so-called functional specification document. That is at the end kind of, let's say, some contract. What do we have to fulfill? And then you and your customer effectively agree on this functional specification document, and only if this is agreed, then you start, because then you know exactly what to deliver and what also at the end to prove to your customer that it works. In that step, the basic requirements are set. In particular, which interfaces do you have? Which functional requirements do we have? And what are expected properties? So for instance, do we go for a high performance design? Do we go for a design with low power? Do we go for a design with low area, which is cost, power, or timing? Good. Then you decide effectively, based on what your functionality is, which algorithms you use, and then these algorithms need to be. Now, let's go through the following steps, most of them, not all of them, but on a little bit high level, with a very simple example. And I take here, this one probably correct. Let me see if this works. No, not yet. I just try to get out how to put it to the second one here. Probably this one. No. That's it. Now I have it. Okay. We start with a very simple example, and my specification is I want to build an AND gate, which should be simple enough that all of you have at least heard of. So we want to have an AND, and so our formal description is, I write it in that kind. So that is what we mathematically want to achieve. Good. Then we need to implement this. So we first need to do an architectural design. In our case, architectural design is pretty simple because we have one architecture that is, we have an AND gate, right? So if we had something more complex, we would have to build some blocks, basic building blocks, where each of the building blocks effectively corresponds to one system part that can be independently implemented. And you need to specify the interface between them. Now, if we want to do this for our NAND gate, then we only have one building block, which is just some interface, some black box. We know we have two inputs, A and B. They are 1 bit wide, and we have an output, C, which is also 1 bit, right? That is, for our specific case, the overall design, because we have such a simple design. If it's more complex, we need to have more. The concrete example here on the slide is that is a module for DES algorithm. DES is an old crypto algorithm, nowadays outdated, nevertheless still sometimes in use. And what we have is actually we have here the module that describes the actual algorithm, the logic behind. We have something for a key. So since it's a crypto module, I already said, I'm from a security chair, so I like all this crypto stuff. So we need some key that is used for this for the encryption of some data. And of course, if we want to have such a building block, we also need some interface. And I decided here to have some RS-232, some UART interface that is just, we have two wires, one wire in, one wire out. I have, later in the lecture, I have also how this protocol works. Not so important now for the moment. On a high level, the engineer working on the specification only needs to know that's our interface we want to implement. This interface has inputs RxTX and output input Rx, output TX. And it has some internal stuff, and then we have another block for the DS and one for the key store. That's the decision we make on that level, not going really into details. Good. Then, in an actual, more complex design, again, not for our NAND gate, we would go into the different blocks and build sub-blocks. That is already done by usually more specialized engineers. So that is the data interface that is provided from the next higher level. So if we go back, you see we have here something like clock input, reset input, data input, data output, some handshake signals. And these things are, of course, also there if we go on the block level, on a smaller block level. That's this part here. And then we have on top, in the other direction, the interface to the key. So also this block obviously has an interface. We have to define how this works. And then we have in this submodule, we have also further submodules. We have, for instance, here this DS rounds, which is, there are some logic functions that do permutation stuff like that. So just some logic operations on the inputs. There is some part which does some key derivation, it's called. It does some logic operations on the key for every round. So that is just a multiple round thing. And there is some control on top, some control block, which needs to control when to do some data transfer, when to input, output data, and so on. So you typically also have some control logic in there. So to keep the long story short, in general, you are not done with having macro blocks. You form sub-blocks, and in each sub-block, you have another round of specification, what you actually have as input, output, and so on. Huh? Good. Why do we do this? Any ideas? So why do we build this? Do we not just start, hey, we know this is our module, we just go ahead and start. So what do you mean by prevent confusion? More precisely? So, yes, so if you want to change something, then you only need to work on the subblock. Yeah? You have an overview over the complete system, which is in different blocks. You can also reuse parts, which helps a lot because you do not, for instance, such an interface is certainly not used only once, but you have this used in most of your designs, something like this. And then you can just say, okay, I use this building block, I just use something I did in the past, and for the rest, I do some new implementation. And another thing I want to add is testability. So our systems today are huge. So they have millions of transistors. You can not test not the complete system exhaustively. That's not possible. What you can do is, if you have sufficiently small building blocks, you can test and verify each individual building block, and then build them together. And on a higher level, at some point, you only do something like random testing, so you only apply random patterns and try to find the corner cases maybe to check, get some confidence that everything works, but you do not exhaustive testing anymore. Good. Okay, when we are on the, let's say, finest level, then we effectively implement or start with the actual implementation. So on this lowest block level, we define finally something like the hardware blocks we want to implement. Honestly, an experienced designer will most likely not draw a block diagram for each and every block. If you do this the first time, it's a good idea to have it. Why? Because when you write or when you describe your block level design, or when you describe your design, you should always have in mind that what you write, usually it's done with some RTL description, so register transfer level description. You should be always aware that what you write is hardware. It's not a software. So if you want to have at some point a multiplexer, then you should describe a multiplexer. If you want to have at some point a flip-flop, then you should describe a flip-flop and not just something that makes logically maybe sense, but is not a hardware. Okay, so to do this, of course, you need a good understanding what actually the algorithm is about. For our NAND gate, we already had this. I just skip on. Yeah, we can do this. Maybe I just put this here and the one here. Okay, so that's just a little bit quick challenge. So we have from somewhere an algorithm that we should implement. And, well, what should it do? It should find some data word in some input sequence. Check. Yeah. So, first question here is, what is if we want to implement something like this in a hardware design, how would we start? Yes. I mean, that is effectively a software description, right? And most of the time, if we want to implement something, then you will be provided with, hey, that's my algorithm, please implement it for me. So, I mean, it's not even software, but from the formal description, it's kind of a software, right? It's pseudocode, which I would write for software, right? So, where do we start? So, first thing to do is we need to understand what it actually does, right? So, what do we have? We have an algorithm that is called scan, that has an input sequence, a data word A, and a data word B as input. And it has obviously some output that is data word out. Huh? So if we just quickly draw this, we can say, okay, we have some block, huh? And this block has 3 inputs. Huh? I just make it a little bit shorter. I call the first input sequence. The second is data A, data word A, and the second is third is data word B, right? All of them are n bit, and then we have an output that is data out, huh? Also n bit, right? That's what we defined. Good. Then, what do we need? Well, we run for some length of an input sequence. So obviously, the input words here come in a sequence. Huh? So from a logic perspective, we have a sequence of words, each n bit, maybe 8 bit, and they go into the thing. And then I want here, if one word is equal to the next word, then the output word is set to A, and we have some flag bit. We overlooked this, I think. So if here flag bit, that is 0. If we have the output word equals A, and we have the output, so if the input sequence is all 1, then we put the output word to word B, and set some flag bit to 1. And if the output word, and in all other cases, we just keep the output word equal to the previous word. We do not update it. Okay? So some initialization for the or what do you mean? You mean some kind of initialization is missing? Can you repeat it? I think I didn't fully. So if this here is 0, right? Then here, so that there is, you're right. So that there is some initialization maybe you would have to add. Maybe I did not fully get the question. Okay, good. So I think if I have this, I think I don't have the solution there. Okay, so so what would we need to implement? Without doing it now that the complete construction here, maybe. What are the hardware components you can identify here? So let's go step by step. We need first, we have a sequence of inputs, and we want to compare 2 inputs, right? So obviously, we somehow need to memorize what the previous input was, okay? So for this one here, we would need some kind of a register, some kind of a buffer, of a memory. So this input sequence here has to be buffered. We need some memory for that. For the output word, we don't always want to update it, right? Sometimes we want to keep the value from the previous step. So obviously, we need another register here, okay? So on a high level, I'm not 100% sure that I will immediately be correct. We have some register bank where we have here some input, the input sequence. For each clock cycle, we have there something else. And we need to compare this. So we need to have some kind of a comparator. This comparator should give us effectively if the input in a specific step is the same as the input in the next clock cycle. So we buffer the input signal. All of this is n bit wide, okay? We buffer the input signal and compare it with the input signal, so the current input signal with the one from the previous clock cycle, okay? That effectively implements this line of code. Agree? Approximate idea what I'm talking about? Just stop me if you are confused, if you say, don't understand, because then I can react. Yeah? If you don't stop me, I just go ahead. So, this is just a register, right? It just stores, and then every clock cycle it updates. We will look into how this internally works and so on. We will have a look at later in the lecture, but for the moment it's sufficient that it stores, and in the next clock cycle it updates. This comparator here, we will also have a quick look somewhere in the lecture, just compares, is the data word I receive here the same I receive here? So this is the previous clock cycle, so it's, let's say, I. Then whatever goes in here is I plus 1. So we have the comparison of this two. Okay, then we have this, let's say, data word output, which should also come from a register. So we have here the data out. If we have here the data out, well, we need to decide in which situation we effectively go into that case, go into that case, go into that case, right? We have three options. How would you multiplex? No, I said already. How would you implement different options in hardware? Different options in hardware usually means we need some multiplexing, right? So we have kind of a multiplexer here that goes here in the input, and the first thing here is effectively a control signal for that. What do we want in case we have these two equal? Let's make like this. I think I have to extend it later. Yeah. In that case here, we want to have in our register the data word A, right? Now, if we want to generate here this, if the input sequence is 1, so effectively we need to take this here, have another comparator, which is compares this with a all one word, or if this should be an actual one, then 0, 0, 0 and 1 bit set. If this is the case, so I just put this here. We call this maybe 0. Yeah, it was stupid, sorry. So if the second bit is 1, the first bit should override it because we always go in the first case. If the second bit here is, if the first bit here is 0 and the second bit is 1, then we want to have here the output word B, data word B, right? That's the next case. So if this is true, if the sequence is 1, then we take the input word B. That's this line of code. And else, so if here is 0, 0, none of the two is set, then we want to keep the values, so we need a feedback effectively of this register in here, right? Okay, what is missing is this flag bit here. What we can do there is, well, we also put this to a register so that it's synchronized with this one here. And this flag bit is 0 in that case, so it should be, just take another color that you can better see where I draw the lines. So effectively it is, we take the value, the result from here, that should be 0. And we take the result from here, that should be 1, right? So if this is 0 and this here is 1, then the output should be 1. Or in all other cases, that should be 1. I need to think of how to realize all other cases. Most likely we need another gate here in between. Probably it's simpler. We can have the simpler. Sorry, we remove that and just put this here there, right? Because in all cases where this here is not set, so an inverter is needed. So in all cases where this bit is not set, the flag bit is set, right? And if this here is true, then the flag bit is not set. So it's just inverted and put to the output. Not expecting that you are able now to come up with something like that. Just what you should learn from that is, how do we start? Well, we first start with having such an interface description. Then we learn what effectively, how does our algorithm work? Yeah, we need to understand it. And then we try to think this algorithm in hardware. And thinking in hardware means roughly we need to decide what is logic. So kinds of comparators are usually logic, kinds of this inversion here is logic. We need to decide what is actually a register or some memory needed. And we decide at which points do we need, for instance, things like multiplexers. Yes, yes, yes. So usually, well, if this is a more complex circuit with many different states, you would usually implement here with this comparator and so on, you would usually implement some state machine.
State machine?
Yes. Yeah. We will talk about this also later in the lecture. If it's so simple as this algorithm, then you can directly derive the control signals from your data. And then you can use this result here for something like this multiplexer. Okay? That was just a quick example how you could approach effectively from I have some algorithm to I now implement some hardware. Okay, now you did something like this. Now you have implemented such a hardware here, such a block diagram. How to continue? So what would you consider the next step after you have decided what you actually want to implement? Well, the next step is somehow to implement it, right? And implementation for digital design usually means description in the hardware description language. So I just remove this and we go to the next slide. Yes, we start here usually with a non-optimized design. So you start with something that you just can develop, let's say, in your head. Optimization usually comes later because optimization means most of the time that your design gets. Shall we discuss something or all good so far? So optimization usually means that your design becomes harder to read, harder to debug. And that's why I usually start with I want to only implement something straightforward, and only if this works, then I start optimization. Good. So I want to go back to our simplistic example, let's say, which is this NAND gate. So for this NAND gate, now we need to write some HDL code. There are 2.5, 3 main languages that are used for that. The one I use here for the lecture is VHDL. Stands for Very High Integrated Circuits Hardware Description Language. So short VHDL. The second one is Verilog, which is very similar to what you do in C from the syntax. And there is an, let's say, advancement of that, which is called System Verilog, which allows to have things like classes and so on. So you can consider this like the C++ of Verilog. Okay. Now we want to write a hardware description for such a NAND gate. the first thing we need to do is we need to describe this black box. That's at least in VHDL, it's the case. Yeah? For that, we now go to RTL level, and in our case, it's VHDL, and we write a block that is called entity, which I give a name, and this entity has some inputs, outputs, so it has ports. Should I try to zoom better? So it has ports, and in our case, we have specified A and B as inputs. We need to tell the tool what kind of inputs this is. Is this a 1-bit? Is this multiple bits? Has this different logic levels? Does it have only 0, 1, invalid, stuff like this? In our case, we use something called std logic, which is just, we have things like 0, 1, X for error and U for invalid. And we have an output C of the same type. So this here has no functionality yet. It's a pure black box description, just as here, telling we have this. And then, well, we need to define how our actual design works. So this is, for our case, pretty simple, of course. Nevertheless, we need a few lines of code. I can also show you later in the tool, but I do this here just by hand quickly. So we have something called architecture, which has a name. What do we say? Okay, we have an architecture, so we have a description of the actual hardware, of the actual functionality, which has some name. It's an implementation of this here. And then after this there comes the actual code. Then you would have some space where you can do some definitions. We don't need this. We have some begin, and then we have some, because it's so simple, the code becomes more or less trivial. Nevertheless, what do we see? We have some begin end. That's the actual description of the hardware. And then we have C. Then we have this strange arrow here. And then we have A and B I've written. So this here is actually no classic, let's say, RTL description. It's kind of called behavioral description. So this here, NAND, is already something that is predefined for this logic, for the signal type. So we do not have to implement that on our own because the example is so basic. But we say, okay, we have 2 input signals, and whatever happens here is assigned to some output C. It's just an arrow to the left. So you write this as smaller equal, 2 symbols. But it's just an arrow to the left. There's also an equal, but equal has a different meaning there. What is the difference? So I just write a second line here. I do this on a table because it's not actually part of this example. Let's say we have here, we take another signal, input X, and I make it differently. I make it slightly different because then it's nice. So we have some signal, should be like this. So we have some additional signal defined here internally, for some reasons, just for a quick to show you something, so it has no practical meaning for the moment. And this is also of the type standard logic. So, and now I make, let me see, we replace here maybe by X, and we write here, so doesn't make sense to write in that way from a logic perspective, but for an example, it's I think pretty good. So if you see this code, maybe first question, did someone write any VHDL code already? Or any hardware description code? No? Okay. Good. But I assume you have written some Python or C code, right? Ah, good. So this is just kind of an assignment. Huh? So it assigns whatever is here to that value. So if you would read that in Python code or C code, what would happen? So if you will read this as C code, let's write this as a, not exactly, not precisely, but as a similar C style thing. We would have, let's say, some function which, for simplicity, we take integer values only. Yeah? We have int a, we have int b, right? That's our inputs. Then we have integer x. We have some additional signal x. Yeah? And we try to do something like, I call this just int c, yeah? The output value c equals a, for simplicity I just take plus, yeah? Because, well, we could also take NAND. What is NAND in C code? So probably something like, maybe we take just plus, huh? It's not exactly the same, yeah, but that's not the point, what the logic functionality behind this, yeah. But I cannot remember what actually, how a NAND is written in so, and then we have x equals b, huh? And return c, right? So, in this code, what would happen? The x is somehow undefined, so most likely the compiler, that should be x, sorry. The compiler would say, okay, if I don't initialize this, in C you always have to initialize, yeah? So in case you do not provide an initialization, the compiler will do something. Yeah? The compiler will most likely initialize it to 0. Yeah? So this here will be C equals A. This here doesn't have any effect. This here is actually just returns A, always. Yeah? That is what this code would most likely do, because we did not initialize. What's here? Now we are in hardware. The things here are signals. Huh? So if we draw the logic of this diagram, we would have, well, we have a NAND gate, okay? This NAND gate has inputs A and X, huh? And output C. That's this line. And X is assigned to B, so X is connected to B. That's perfectly fine, right? Because this is not a classical programming language. Huh? It's a hardware description language. And the difference, in other words, is if you operate here on signals, you can also operate on variables, would behave like that. But if you operate on signals, like here, you have this kind of assignment operator. And this kind of assignment operator does not matter what the order here is. So all of these lines are virtually processed in parallel. So of course, if you do the simulation on a computer, it has to do something sequential. We talk about the simulation stuff later. But virtually, from how you think about this, all of this here happens fully in parallel. If you want to have something not in parallel, you need a register, okay? Because you have a circuit, and the circuit is evaluated fully in parallel. Of course, you have some runtimes internally and so on, but if you neglect this, then fun? Well, we have to separate this part from that part. This part here is a description. Huh? This description is then, in the next step, compiled, just as you would compile here for some processor, you compile here for some circuit. Huh? And the tool that compiles makes out of this a circuit where it just says, okay, I have an AND gate, just as I did here. I have an AND gate, I have A, I have X, I have C. I have another assignment here, which is B. And B is, or X is assigned to B, so we need this connection. So this is what the tool effectively makes out of that. This is how it works, or what happens in hardware then. If you want to simulate this, you need to do something else. So of course, if you want to simulate and just go through this line by line, it would not work. You would have, this is undefined, I'm done. Okay? I will come, well, we can also talk about this now, but I think I come back to the simulation later. Okay. Questions so far? So, what we have now is this kind of a description. If you're done with that, what would you do? Well, since you never worked with RTL, you with hardware description, you most likely also never build a circuit. So the next step is we now synthesize this into gate level, transistor level netlist. This synthesization, well, you have to provide some inputs, you have to provide some additional data, and so on and so forth. But this synthesis effectively is done by the tools themselves. But at that point, now it becomes important what we specified at the beginning, where I skipped a small thing that you need to specify, namely the targeted platform. So if you're talking about hardware implementations, then there's always two things that you can make. The first, what you can make is you can implement some ASIC, which stands for application-specific integrated circuit. That is, you really want to build a chip. So you want to go to a fab, you want to get something manufactured, and you have your own design at the end coming to the chip. The other side is you go for some FPGA, which is so field programmable gate array. This means you have a fixed circuit already, which is to a certain extent programmable. How this works, I will later show you give you some insights. So this is the main decision that is relevant for us. There is another decision you can make, namely you go for some microcontroller, some software implementation. But then you are out of circuit design at the end. Of course, if you go for something like an ASIC, also for the FPGA up to a certain extent, you can also make decisions like to which extent do you implement stuff in hardware, to which extent do you implement stuff in software. If you compare hardware versus software implementations, what do you think, where are the benefits and drawbacks of a software versus a hardware implementation? Break time? Take for your break what the difference between hardware and software implementation is, and we continue at 11:15. Huh? 15 minutes. Okay, let us continue. Okay. Before we start with the break, I had the question if you have any idea what the benefits / drawbacks of hardware versus software design implementations are. Is there any idea now what could be a benefit, let's say, of software over hardware and vice versa? Any guess?
The hardware, you find out
Yes, so the big benefit of software is that you are flexible. Yeah? So you can change it easily, you can update it easily, even if it's enrolled. What is the benefit then of hardware? So why should we then implement something like an ASIC?
Are you saying that for hardware, ASIC is preferred?
No, the question is if we now want, if we say software is so good because it's flexible. Yeah? And indeed that is a big benefit, yeah? Because if I have nowadays, if I have, don't know, some bug in my software, then I just enroll a new version of the software and then I'm done. Yeah? If you have a bug in the hardware of your car, then you need to drive to maintenance and you need to exchange something. Yeah? Obviously, software update is easier. Yeah? So why should we build something in hardware at all? So we run software usually also on hardware, of course, which is built to be flexible. So we can perform different tasks. ASIC is always specialized, but that's also a benefit of software, right? So still, why hardware? If you're really, not precisely. So the point is, what happens in your software? If you run a program as I've written before, yeah, so just a few lines of code, then that means that you have a processor. The processor loads data, processes an operation, writes data back, and does this many times. Of course, there's pipelining place and, which speeds it up, but there's a lot of clock cycles to perform relatively simple operations. That means it's comparably slow, and you need a lot of operations, meaning you need relatively much power. So, in that sense, hardware is better because we can build a dedicated hardware for a specific task that is super fast for that task and needs hardly any power. But of course, then we are specialized for that task. So that's effectively the trade-off we have to make. Do we want to have something specialized, hard to update, hard to maintain, but very performant? Or do we want something that is very flexible, good to update, and easy to maintain? It's not always the same decision, right? That is always a trade-off you have to make to rethink for each and every new design. Does it make sense that I build this in hardware? Now, if we talk about FPGA, that's somewhere in between, I would say. So you have not the performance as an actual ASIC, because it's not specialized for a specific task, but it's still implementation in hardware. So it's faster than you can get in software usually. On the other side, it's programmed, so you can, up to a certain extent, also update the program. Update just, you reconfigure the hardware. Okay, now if we look into the slides, then effectively where we are now on the slides is, I just quickly show in this one here. So where we are on the slides is actually, we have done our functional design, we have done the RTL description, and now go for what is called usually circuit design. Circuit design can be split into two parts. It's gate level design, so we process from an RTL description to a gate level description, and we go from a gate level description to an actual transistor level description. Okay? So let's see how this works for our NAND gate. If we first exclusively talk about ASIC, then for the ASIC, well, a NAND gate is a NAND gate. Yeah? So we have on a gate level, we have our NAND. Usually, if you do an ASIC implementation, you also need to define what type of NAND gates you use. So for instance, that is something I just randomly picked up as a name. I think that's indeed taken from some open source technology, but what you typically have in an ASIC design is you need at that step where transit from the RTL level to the gate level, and then further to the transistor level, you need something called a PDK, process design kit. This process design kit defines the physical properties of your chip that you need for simulation, for setting up all the transistors on the chip and so on. With this, you usually have some standard cell library. Standard cell library means if you want to implement a NAND gate in a specific technology, someone, usually some analog mixed signal designer, has to sit down and has to define a NAND gate in this technology has to have these transistors at that position, has to have disconnects in that layer of your metal stack, and so on. That is what you have to define to have a reasonable gate at the end. So, and from, there is not a one-fits-all gate, but usually there are different ones. So for instance, you have something like LP here, low power. So you have a gate that is dedicated for low power design. On the analog level, just designed for that. Maybe smaller sizes, something like that. You may also have something like an HP for high performance, which is then usually more power hungry, but faster. Something like this. So you have to decide which gates do I actually want to use, or you leave the degree of freedom to decide which gates are used to the tools and set some optimization directions. So that is what you can do here. Now, I continue with the ASIC side first, because it's a little bit different for the FPGA. Now we want to do a transistor level design. If I implement a NAND gate on transistor level, how does this look like? Did you learn this already in the previous course? I think so, right? So maybe we just quickly recap it. So we have a CMOS technology and we want to implement a NAND gate. What do I have to draw? So maybe we start with a simpler one. How in CMOS technology does an inverter look like? That's the inverter circuit symbol. So this is what we want to implement, and we need a transistor level description of that. Transistor level. So how are transistors connected here to implement this in a CMOS technology? Was there any class where you did this? No? Not at all? Yes? So you never did this? Because it's, well, maybe to explain to you, yeah? So every year it seems that the classes have a little bit different pre-knowledge when they come to this course. Last year people have known this, did less Boolean algebra stuff. The year before people did not know this, had less Boolean algebra stuff. So it's not always the same what I can expect. So if you don't know this, no problem, then we don't need to know everything in depth, but I want that you have something in mind what we're talking about. And I can explain it, but I need to know how much do I have to explain. So we have effectively, you know, PMOS, NMOS. PMOS is if you have a 0 at the input, then you can think about this like a switch. And the switch for the PMOS, if you have 0 at the input, is, think a second, is open. So it's closed, so it's connected. So what is open, what is closed? So it's connected. For the NMOS, it's the other way around. How this works on a physical level, we just ignore for the moment at least. Now, if we want to implement something that inverts, if I build a, let's say, very simplistic switch model, then I need effectively an input, let's say that's X, that's Y, and this input should go to, let's say, some switch, which I need to think how I draw it best, and a second switch. So this here is ground, this here is supply, VDD, this here is Y, and this should go, okay. If the input here is 1, then we want to connect, we want to close this here. We have a connection to ground, and the output is 0. If this here is 0, this switch is open, this one here is closed, we have a connection to VDD. That's what we want to implement. CMOS, complementary MOS, we have both of this implemented as MOS technology. So what we need is, we need something that here opens if we apply a 1. So the switch opens, so it's disconnected, and here something that closes if we supply to 1, right? So what we have is, I draw always the PMOS like this. We have another, which is an NMOS, and then we have here X and here Y. Now on a physical level, if we apply here VDD, this here becomes conducting, because some electrons go there, blah, blah, blah. And you can connect from Y to ground. If you apply a 1 here, then this here is not conducting, because it's a P channel here, and you are disconnected from here. So in that way, we have the one direction. If this is 0, then it's the other way around. We are disconnected here, we are connected here, so Y goes to 1, right? Okay? Makes sense? So you can think of a PMOS transistor as a switch that is default closed, for an NMOS transistor as a switch that is default open. On a, let's say, rather computer science, not so much electrical engineering level. Of course, there are a lot of different additional effects. We may talk about the one or the other later, but for the moment, that's enough. If we, now we want to build, so one sentence more. All of the of our CMOS gates are inverting. What this means for an AND gate, I can state in a minute. Now we want to build an AND gate, not AND. So what do we need? We need at the output something that is logic 1 if one of the inputs is 0, right? So we have 2 inputs and we need to connect. So I just write the truth table. Let's say we have x1, x2, and output y. If one of the 2 inputs is 0, we want to have a 1, right? And if both of them are 1, we want to have a 0, right? Okay? That's what we want to implement. So if we want to have a 1, as soon as one of the 2 inputs becomes 0, we need for the 0 2 PMOS transistors, right? So we have this here is x1, this here is x2. So we are not yet complete, but if this here is VDD and one of the inputs at least is 0, then the output y here is connected to VDD is 1, right? Good. Then we connect, if both are 1, we want to have the output to be 0, right? So if both means there should be some serial connection. Yeah? So we have one NMOS here connected maybe to that one, another one connected here. Yeah? Now, if these two are both connecting, so the inputs are 1, we have a path from Y to ground. We have no paths from VDD to Y. Yeah? So we are at ground, right? Okay. Maybe we can quickly also think of how would a NOR gate look like. So this here is NAND. We make another here for NOR. Maybe I start a little bit further up. For the NOR gate, what do we have? X1, X2 can have, again, from a truth table perspective, these inputs. We want to be 1 here, 0 there, right? That's the definition of a NOR, okay? So, proposal what I should draw in transistor logic for this NOR gate, if I want to implement this functionality. So, we have Y, we have VDD, we have ground. When do I need to connect to ground? The NMOS, you mean? NMOS. CMOS is the overall thing. Yeah? CMOS is complementary. Complementary means we have P and N, but the idea is correct. So we have 2 NMOS transistors in parallel now, probably. And then, well, with the PMOS in series, right? Oops. And then we just need to draw some connections, and one is X1, the other one is X2. Okay, I skipped the XOR because that is a little bit more complex. If I want to implement an AND gate, what should I do? Exactly. So all of these circuits are, all the CMOS circuits are, gates are inverting, meaning you cannot just straightforward build an AND gate. So you build an AND gate and put an inverter afterwards. Good. Usually your NMOS transistors have a better characteristics, switching characteristics than the PMOS, meaning that NAND is preferred over NOR. NAND has the benefit that is usually smaller, yeah, and faster. If you want to implement an AND gate, then you can just add the inverter, but that gets also larger. So to keep the long short, you can effectively try to use as many NAND gates as possible. Nothing you care about as the digital designer, to be honest. As a digital designer, you write your RTL code, and then you do the synthesis, and then the circuit does the tool does something. Yeah? You just need to have in mind at some point what actually happens in the tools, what happens in the actual design, to understand why do I do the implementation on a higher level in a slightly different way, and the design gets more optimal. That's why you need to have a rough understanding at least of what happens then in the transistor level down, just to understand why do we do things in a specific way on a high level. Okay, so I remove this here, and then I draw it on the other side because I want to have it on what I give later to you. Okay, we have here the NAND gate on a transistor level. So we start with our 2 PMOS connected VDD. We have the 2 NMOS connected to ground. And if we think about this here, this was actually A, B, and C in our previous slide design. So if we now go into the transistor level, we still have A, B, and C as the nodes that we see from external. Yeah? So it's still all the same, it's just another level of abstraction. Okay, now before I go to the next step, and to the FPGA. Let's see where we are. So we said we are in the circuit design. We can implement our gates, whatsoever, our logic now on gate level, where we have then only logic gates and registers at the end. Yeah? And then, what is the benefit of this? Well, we are now already closer to what we finally will see in the hardware. Yeah? So if we now simulate, our prediction will be more accurate. What it means for simulation, we can also see in a second. Okay, then we are still not there. So the next step is the physical design. So we were already on the gate level. We have already designed which gates to use, but now we want to bring this onto an ASIC. And if you want to bring it on the ASIC, what do we have to do? Well, we have to decide which parts of this silicon, of this wafer, have to be doped, which not, where do we need polysilicon, and so on and so forth. So if you think about an NMOS transistor, then as an example, then roughly speaking, we have, well, some bulk material, right? And on this bulk material, you implement some diffusion areas. Yeah? So you have p-dopant base material, and you implement here, depends a little bit on the technology, how this precisely looks like, but generally you have something like this. You have here some n-dopant, and here some n-dopant connection, commonly known as drain and source. Then you have to put some oxide on top of this, right? And then you have a gate where you need to say, okay, here you have the metal, respectively the polysilicon, okay? So this is kind of where we want to come from if we see here such a transistor, okay? How to do this, how to tell a fab that this is what we want to have at that position. That's the task of the physical design, actually. So physical design means mapping this here into some layout and to do the routing. What do we need for that? Well, we need to say, okay, at that point, we need some N plus region. At that point, we need some oxide, and then we need to define where we have the connections. Or actually, we need to define where the gate is, not where the oxide is the same. Okay? So this is what we actually need to tell the fab. Now, how to go there? Of course, in a practical setting, you have the tools for that. So the tools will do most of the stuff. Nevertheless, I think it's useful to see at least once. That was not what I wanted to do. What I wanted to do was this one here. So I think it's useful to see at least once how such a process, or how this translation actually looks like. So, good. So what we do now is effectively we go for layout and routing. And the first step is normally, that's of course for our NAND gate, it's not needed. Still, I write it here. So I call this macro placement. What does it mean? You define effectively a chip area. So if you want to design a chip, then usually we have a specific area where we need to put our stuff. On this area, you define an I/O ring, or besides this area. So we have a specific part You have corner cells where nothing happens, and then you have here something like pads, usually with a little bit of space in between, which gives you effectively the I/O ring. So, why is this needed? Because later, when you manufacture the chip, then you want, of course, to package this into some package, and you want to connect your internal chip to the external world. So you need to do the wiring from this internal pads to the pins of your of this black chip, black thing that you receive somewhere if you buy it. So this connection needs to be done. That's where we need the I/O ring for. This I/O ring needs to be designed so that we have VDD connects, that we have ground connects, that we have clock connects, and then the regular I/Os that we want to have for our logic. So this is what we have. And then we need to define, of course, how large this is. There are specific design rules depending on what your packager can do, what your process can do, and so on and so forth. We just skip all of this just that you have here it once. Okay, now we are done with this. Then the next step is usually that you place manually your large building blocks in a circuit. Large building blocks are things like, say, analog interfaces or SRAMs. So, large building blocks means we have memory blocks, which are usually not designed by designer, but generated and then treated as black boxes, kind of. They have to be placed somewhere. You have I/O, have analog interfaces, for instance, amplifiers, stuff like that. That is specialized hardware that comes to you as a back-end designer just as one macro block, and then you integrate this into your overall design. And these are things that are placed by the designer because then, well, for the tool, it would be very complex to do that. And you have an idea how your overall design should look like. And then you place them more or less just so that you have a lot of area for the logic left, and for the routing. So, rough rule of thumb, just that you hear it once. Okay, so this is what you usually do manual or partially manual at least. All define some spaces around that so that you do not come too close with the logic to some blocks and so on. And then what is usually done by the tool, or it's already partly predefined in your standard cell library, is something how effectively this mapping here then looks like. And for that, I make one example now for this NAND, where you effectively, we start with, what do we start? It's actually a little bit random what I start with, but doesn't really matter. We take, for instance, A and B as a starting point. So, A and B, I draw this in green. And A and B means, well, we connect to the gates of our PMOS and NMOS transistors, right? A, obviously, everything is connected. B, obviously, everything is connected. So we can just have two stripes of connection material. How long should I draw this? Maybe a little bit longer. One of them is A, the other one is B. And this is, just give a little legend here, is usually done in polysilicon. Just connecting material. The lowest level usually is polysilicon, and that's what we use for here. Then, below of this, we need effectively some gate and drain P and N diffusion area, yeah? For drain and source. Drain and source need some diffusion area. We draw the PMOS on top. Yeah? So I visualize this with this purple color here. So this one here should be P diffusion. And for the fab, we do not have to separate this, because if it's under the gate, then anyhow it is not manufactured. So we can just draw one stripe here, and oops, it should be stripe here, but I did a minor mistake, which I can still correct, because I need a second one, which is N diffusion, and the N diffusion should go here, and the P diffusion should go here. So what do we have by now? We have effectively, with this here, we have from our overall circuit an input A that connects to one PMOS transistor, and we have and to one, at the moment, independent NMOS transistor. That's effectively this part here. The gate is connected. This here below the gate is ignored. This is P diffusion, N diffusion, N diffusion, P diffusion, P diffusion. I cannot see the legend here. I should move this a little bit up. So that is the part that we have here. P and N diffusion, which is effectively we have the connects of the inputs for the for source and drain defined. Then we have B, which is another input. This goes to for the first place here, unconnected NMOS, and for the moment, unconnected PMOS. And by the way this is drawn, one connect of the two transistors, we did not decide what is drain and source. Here is already connected. One connect of the drain and source here is already connected, right? So, without any further things to do, we effectively have one connection already in place, and we decide that's just this one here. That's effectively just a decision because it makes sense, and we say it's that decision. So this is where we are, just by drawing these few lines here. So we have the two transistors, which are effectively, or four transistors, which are 1, 2, 3, this one here, and 4, this one here, right? And here, effectively, the drains of the two transistors are already connected. Now, we need to go ahead and make one small addition here. Namely, I state later what this is, one here and one here. Good. So what is missing? Effectively, just some wiring, and we can do this in the lowest metal layer, for instance. So we decide we have here VDD and ground and all the output C. And we start with, let's say, VDD, and that is, how do I write this? Maybe down here, this is metal. Then I do one connect down here. I do another connect here, and I need a last one here. So far, it's only some metal over the lower levels, but no connection. So to have a connection, we need here some actual connect. So this here is effectively, which means we have some via which goes down. So what does this implement, what I've drawn? it implements a connection here, right? That's what we have. Then we do the same thing for the ground. So we start somewhere here. Blip, blip. I need to correct a tiny little bit because now in the way I've drawn it, but otherwise this gets so crowded. The way I've drawn this is effectively that we have here B and here A, because I connected ground to the one connect of A, right? Which is I connect here to ground. What is missing? The connection here in between, right? So what I need to add now is a connection between the second interface here of the PMOS and the NMOS and the output. So I need actually to draw this here, right? Which is now I connect from this point here to that point here. And at the same time, this here is my output C, right? Okay, so this is kind of how it looks like. So if you would implement it with a tool, the tool will most likely do it automatically. But if you do it in a full custom design on your own, it would look something like this. Now the manufacturer would go and say, okay, I start my implementation, I put the basic material, the bulk, and then I implement here at that point, here and here and here and here and here, the corresponding diffusion parts. On the green lines here, I put my oxide and the metal bit above, and then I connect, or the polysilicon above, and then I connect my metal and have the contact and specific position, and that's it. So it's really like a figure. It's usually called GDS2 files still, which is a format for figures, and this is transferred then to the fab, and the fab can manufacture it based on it. Okay, there are two things drawn I did not talk about so far, namely these two. So what are they good for? Actually, if you think about this here, this NMOS for instance, it would mean that you have here P plus dopant and a connect to VDD, no, to ground. Is this? Just need to be careful that I do it correctly. Yeah. So why is this done? Well, it is actually to have any, well, if you think about this transistor, you have not 3 connects, you have actually 4 connects. Yeah? Namely, gate, drain, source, and bulk. Yeah? The bulk connect is usually fixed, but to avoid currents there to some other gates, you frequently have an additional pin which is connected then to ground so that any currents going into the bulk can go somewhere. Yeah? And that's why we have here this, this additional connection. Okay, good. That was the design flow for the ASIC side. So we have, at the end, we started with an RTL level description, and we went all the way down over transistor level to some figure that can actually go to the fab. Before it effectively goes to the fab, here, before it actually goes to the fab, there are some tests. So we did this here, which was this layout we have drawn. And now, well, there is some step before the actual fabrication, which is firstly verification sign-off and layout post-processing. So what does this mean? This process of implementing the design is fairly automated. So most of the stuff is just done by, you have this ready and click a button. But there are different things that can happen. For instance, you can have very long wires that may, during manufacturing, cause that there's some charges collected and destroys your circuit. Then you need to cut them down. That has to be done manually. Such problems are usually visible via these DSC checks, design rule checks. These design rule checks look, are all the spaces okay? Is everything as defined for the fabrication process so that the design, the layout you have drawn is actually manufacturable? And then it gives you feedback. But the fixing of the DSCs is usually manual work done. That's also some ugly work, I would say. So if you're experienced, then it's okay, but if you have a new technology and no idea what the DSC warnings mean, then you have to check them violation by violation, and that's, well, a lot of work. That's one part. Then I continue here. You may have the case that you initially thought your design would be okay from the timing perspective. So you have a target frequency and you think, okay, well, that should work out. But after the placement and routing, you suddenly get long wires. You suddenly have a longer critical path, also a longer runtime from one register to another register, than what you are allowed to have for a specific frequency, right? So timing properties we will discuss a little bit later. To find out if something like this happens, you do static timing analysis today, sometimes statistical static timing analysis, but mostly static timing analysis, which really checks under specific simulated, of course, conditions. So for specific temperature conditions, for specific too low, too high voltage, how does your circuit behave? Does it fulfill all your constraints that you put? This is a check you require usually, or another check is this layout versus schematic. A similar check can also be done here between schematic versus the RTL design. The purpose of this is, well, you implement something, your simulation tells you it does what you expect to do. Then you press your button for synthesis, for layout, and you end up with a layout. And for some reason, you overlooked some corner case, and a lot of things are optimized out. Usually it's a designer mistake, not a tool mistake. So how can you trust that whatever comes out here is the same as above there? The problem is, the farther you go down, the more precise your model is, the more accurate it is, the closer it is to your actual manufactured circuit later. But at the same time, the harder it is to simulate, because there are a lot more information, and running a physical simulation, well, if it takes, let's say, minutes, seconds on a functional level, on RTL level, then on the physical verification level, you can say the same simulation takes minutes, hours to years. So you can just not simulate everything what you can simulate before. Later, you cannot test so good. That's the reason why I need to check, is what I have here still what I expect it to be? So you take the layout with all the connects, with the routing, and ask the question, is this functional equivalent to what I have here? That's this LBS. Good. Then you press effectively another button to do here this layout post-processing. So that is something at least we at university do not ourselves. So if we do a chip manufacturing, we end actually here with a sign-off. Then sign-off is the point. It's DSC clean. It's manufacturable. We have a GDS2 file. We give it to the fab, and then the fab does some post-processing. That can be, for instance, if you have SRAM implemented, that might be IP from the fab that is also here not fully there on a physical level. Then it needs to be replaced at that point by the fab who actually has the IP and knows what has to be there. So in that sense, here a little bit more can happen, and then the actual fabrication happens. So build your actual silicon, and afterwards the chip comes back from the fab, goes to a packager usually, who does the wiring, so the bonding of the chip, package the chip, and gives you, well, the actual chip with housing back, and then you can test that what you had is still okay. Of course, also you can do some testing in the chip directly, so with some needle probes and so on, all not so much of interest for us. Okay, that is how it works for the ASIC. What changes now if we do it for the FPGA? So, where did we start? We started with a NAND gate. Now on FPGA, we do not have something like a NAND gate. We have predefined logic, predefined connections, predefined circuit. I just need to stop myself. So, of course, you can still say, okay, give me some gate level netlist, then you will get something like an AND gate, just as for the ASIC, with ABC, but it's not dedicated in any way to a specific low power or something like this. It's just a logic description of what you have anyhow. Then we also don't have a transistor level. So what effectively means a NAND gate on FPGA? Well, what you have on FPGA are so-called lookup tables. So the next level here would be something like a lookup table. More general, maybe I write this, BL selection, and BL stands just for basic element. This is, let's say, Xilinx language. So other FPGA vendors may call this a little bit different, but they mean all the same. In our case, we use a lookup table, LUT. Lookup table is, concept-wise, we have some LUT, A and B, and it should output some output C. Logic-wise, we have something, in that case, we can draw it as a simple table here. We have A equals 0 or 1, B equals 0 or 1. And then we just put here the values of C, and C is 1, 1, 1, 0. So I just, maybe to visualize this here is C. So lookup table, that's where the name lookup table also comes from. We look up at position A equals 0, B equals 0, and no C equals 1. That's the basic idea behind that. From a circuit level perspective, how this is implemented on FPGA is, that's highly protected IP, but from the best of our knowledge, there are some patents which go in this direction, that's the reason. It looks like this. You have a fixed depth multiplexer tree. In case of Xilinx FPGAs, it's usually 6 levels. In our case, I just use 2 because I don't want to draw too much. So the output here is effectively C. We have fixed 0 and 1 here, fixed 0 and 1 here. We have fixed values routings here. The one selects this one, the other one selects these two, which we can, in our case, then connect to A and B. And that's effectively now where the magic is. You have here some memory, some SRAM at the end, which is programmable. So without the letters in place, this is what you receive from your FPGA vendor. And then what you can do is you can select what are your inputs and outputs, and you can select what is programmed in this memory. So in our case, we want to implement an AND gate, meaning if we have here A at 1